Well, what do you know? Do you think MS diagnostics might even change some from what we've had in the past 20 years? Well, hello and welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam and I've been living with multiple sclerosis for 38 years. And I never get tired of researching new topics because you always learn something. And I just recently saw an article that I found very interesting. I'm going to share with you in a minute. But when you think about most of the articles that we see, they have to do with testing of therapies that we already know about, like Ocrevus or rituximab, to see how people are doing after a long period of time. There is great value in those studies. I'm not knocking that. But I think it's been quite a while since I've seen something new in the diagnostic area that takes advantage of new technologies, advances that we've made since the MRI. The article that I'm going to be talking about relates to many other articles that discuss the same thing, and it has to do with using machine learning to understand what the possible prognosis and long-term outcomes are for people with multiple sclerosis. Quite fascinating. I hope you'll agree. Well, here's the article. It came out of the Medscape Topic Alert newsletter that I get email notifications on. And this just came out. The date's a little cut off there, but it's Monday, May 1st, 2023, so it's today. It's called Machine Learning Can Predict Primary Progressive MS Progression. That caught my attention. It originally came out of MD Edge News in their conference news section, and they're reporting on the AAN conference, the American Academy of Neurology. So all good stuff. Let's find out what they have to say. So in Boston, it says, in patients with primary progressive MS, machine learning can predict progression with reasonable accuracy on the basis of the blood transcriptome, according to a proof-of-concept study presented at the 2023 annual meeting of the American Academy of Neurology. The accuracy was sufficient for the lead author of the study, Michael Gurevich, PhD, head of the Neuroimmunological Laboratory in the Multiple Sclerosis Center of Sheba Medical Center in Ramat Gan, Israel, to say that it is already clinically viable, even as the tool is still evolving. We are looking at larger sample sizes to improve the accuracy and generalizability of our model, but we can use it now to inform treatment decisions, Dr. Gurevich said. In patients with primary progressive MS who have a highly variable course and who doesn't, the model predicts a disability progression with an accuracy of approximately 70%, which is really amazing, according to the data he presented. He said he believes this is already at a level that is meaningful for a risk-to-benefit calculation when considering treatment. It says here, this is the thing that I found really interesting. It's a totally different way of diagnosing multiple sclerosis. It says machine learning analyzes blood samples. The study pursues the concept that the genetic information governing highly complex pathophysiological processes is contained in RNA sequencing, while multimodal omics generate data that are too complex for human pattern recognition. There is a growing body of evidence, including that provided by this study, to suggest that machine learning can employ these same RNA profiles and predict disease activity. In this study, blood samples were collected from patients who had participated in the Phase 3 clinical oratorio trial that led to approval of ocrelizumab for PPMS. Analyses were conducted only on blood samples from those randomized to placebo who, like those in the active treatment arm, were evaluated at baseline and at 12-week intervals for more than 2 years. After development of a prediction model and creation of a training data set, machine learning was applied to the deep sequencing of the blood transcriptome data for predicting two endpoints. One was disease progression at 120 weeks, defined as a 1 point or more increase in the Expanded Disability Status Scale, our good old EDSS, among patients with confirmed disability progression for at least 12 weeks. You go on to say the other was change at 120 weeks in brain morphology, defined as a 1% or more reduction in brain volume. The peripheral blood samples were subjected to RNA sequencing analysis using commercially available analysis techniques. The prediction model for the disability endpoint was based on data generated from the blood transcriptome of 135 patients, of which 53, or 39%, met the endpoint at 120 weeks. The prediction model for the change in brain morphology was based on the blood transcriptome from 94 patients, of which 63, or 67%, met the endpoint. On the basis of 10 genes that most significantly differentiated those who met the disability endpoint from those who did not, machine recognition of patterns after training was able to predict correctly the outcome in 70.9%. The sensitivity was 55.6% and the specificity was 79.0%. The positive and negative predictive values were 59% and 76.8% respectively. On the basis of the 12 genes the most significantly differentiated, I think it was supposed to be that. On the basis of the 12 genes that most significantly differentiated those that reached the endpoint from those who did not, machine learning resulted in a correct prediction of outcomes in 75.1%. The sensitivity was 78.1% and the specificity was 66.7%. The positive and negative predictive values were 83.3% and 58.8% respectively. And unless you're a scientist, a lot of those percent things don't make much sense, or maybe you don't even care. But I think the big number here to be excited about is the success in the prediction of outcomes. Here we've taken a tool that is already available. It's not like they had to develop the machine learning program. It looks like it was already developed and it was used for other purposes. They took that tool and they started using it to look at the blood of patients who had tested positive for primary progressive MS, and they wanted to know, what is the likely prognosis? Are they going to deteriorate? Are they not? And their success outcome, based on what that machine learning was able to do, was 75%. And that is actually quite amazing, especially for something that's really pretty much in its infancy. They say here, if further validated by others and in larger studies, this type of information could play a valuable role in primary progressive MS management, according to Dr. Gurevich. Now that there is an approved therapy for PPMS, as we know, ocrelizumab and others are now approved for that, it can help clinicians and patients determine whether to initiate treatment early to address the high risk of progression or delay treatment that might not be needed. Now that's interesting. That could be dangerous, I suppose, depending on how those results are interpreted and what the physicians make of it and what the insurance is willing to cover, etc., etc. With every advance, there's always disadvantages, right? We always have to be careful of that. But I'm really quite interested in this technology itself. It is a completely different way of looking at your MS and what your likely progression is. If you think about the MRI, we don't actually know from looking at the MRI what the likely progression is. We can look at a moment in time, how many lesions you have, how much your brain may have shrunk since the last time you had an MRI, but we can't necessarily predict the progression. What they're saying here with machine learning is that they might actually be able to predict the progression with enough accuracy that the treatment that you get would be more targeted. And this could actually be really helpful for us. As they say, it's a useful tool. In the field of MS, most of the studies performed with machine learning have focused on the analysis of radiological images. However, others are now looking at the blood transcriptome as a potential path to better classifying a highly complex disease with substantial heterogeneity, and that means difference or variation, in presentation, progression, and outcome. For example, machine learning of the blood transcriptome has also shown high accuracy in the diagnosis and classification of MS in patients with clinically isolated syndromes. So you'd go in not even having been officially diagnosed with MS. You have one incident, and they're saying that they can use this tool to help definitively diagnose MS. It says one study reported in Cell Reports Medicine was led by Cynthia Farney, a PhD, Institute of Experimental Neurology, IRCCS, San Rafael Scientific Institute in Milan. And I won't continue on with that because she's pretty excited about this. She's doing something fairly similar to this, and she's getting similarly exciting results. And I think that's the key thing that we need to know. But of course, when I see something like this, I'm very interested to know how widespread is this kind of research? Is this one of a kind, or are there others who are validating this kind of application of machine learning to the diagnosis of multiple sclerosis? So I went out to my search engine and I searched for machine learning PPMS. And I got quite a few results. I started to scroll through them. And the first thing that I encountered is clearly, while it might be posted in a different source, it's clearly discussing the same research. It's out of Boston. It's talking about the AAN conference, the ACTRIMS conference. So I'm scrolling past that. And this one too. I'm not getting what I'm looking for, which is validation that there's more than one set of researchers coming to a similar conclusion. And again, this is the same thing. This is the same thing. And this is not related, I don't think. And this is not related, I don't think. But then I get this article out of Nature, identifying multiple sclerosis subtypes. And we will go ahead and click on this in a minute, but I just want to say that back when I was working at a scientific research laboratory, there were two publications that were kind of the holy grail. Everybody was hoping that they would get their article published in. They're more of a general science nature than, say, a lot of the journals that are specialized for people in a certain field only and usually aren't very widely read. But Science and Nature are two journals that are widely read. They publish a wide variety of scientific articles. But what's really unique about those two and what makes them so elite, if you will, a cut above the others, is that they are peer-reviewed. And even though they cover a wider range, they have the same scientific rigor and they're very difficult to get published in. So if you get an article in Nature, that is a very impressive thing right there. Well, let's go ahead and click on this. The article is titled Identifying Multiple Sclerosis Subtypes Using Unsupervised Machine Learning and MRI Data. So they're using it in conjunction with MRI, it looks like, instead of with the blood, which I like because what that means is they're coming to similar conclusions using different methodology to get there. Let's take a look at the affiliations of the authors, because as we know, the more countries that are involved, the better. And the last one was based out of Israel. But if we look at the author affiliations of this one, here's the lead author, and he's out of the Queen Square Multiple Sclerosis Center, Department of Neuroinflammation, UCL Queen Square Institute of Neurology, Faculty of Brain Sciences, University College London in the UK. And that makes me think that there's no way that Professor Giovannoni would not know about this research. And so I'm curious to know if he's ever going to say anything about it. And that is another piece of data that I appreciate knowing, that there are researchers in multiple countries looking at the same technology. and they're coming to similar conclusions about whether it shows promise. Here's their abstract. Multiple sclerosis can be divided into 4 phenotypes based on clinical evolution. The pathophysiological boundaries of these phenotypes are unclear, limiting treatment stratification. And we know all too well what this is all about. It is unclear, and it's very difficult to know for sure when a person is quote-unquote transitioning into progressive MS from relapsing MS, for example. I've had my own experiences with that and the consequences thereof. Machine learning can identify groups with similar features using multidimensional data. Here, to classify MS subtypes based on pathological features, we apply unsupervised machine learning to brain MRI scans acquired in previously published studies. We use a training data set from 6,322 MS patients, that's a big sample, to define MRI-based subtypes and an independent cohort of 3,068 patients for validation. Based on the earliest abnormalities, we define MS subtypes, and this is different, as cortex-led, normal-appearing white matter-led, and lesion-led. People with the lesion-led subtype have the highest risk of confirmed disability progression and the highest relapse rate. People with the lesion-led MS subtype show positive treatment response in selected clinical trials. Our findings suggest that MRI-based subtypes predict MS disability progression and response to treatment, and may be used to define groups of patients in interventional trials. So same kind of thing. They're going to be able to use this predictive data to help with treatments for people who are told that they have MS, and how successful such various treatments might be. They say here in their introduction, there is a pressing need in neurology to define disease phenotypes based on their underpinning mechanisms as an important step towards stratified medicine. The consequences of redefining disease subtypes based on biology rather than on clinical grounds alone are that clinical trials should be better able to recruit patients who are likely to benefit from the medication under investigation. New technologies such as artificial intelligence and machine learning can evaluate multidimensional data to identify groups with similar features. Such methods applied to visible abnormalities on MRI scans have great promise in classifying patients who share similar pathobiological mechanisms rather than common clinical features. And then they talk in general about what MS is. And down here at the very last sentence of this paragraph, they say phenotypes, so how something looks, and their descriptors are routinely used in clinical trials to select patients and to guide treatment assignment. And I think we all have had experience with this. Imaging, immunologic or pathological investigations often show more similarities than differences across the MS clinical phenotypes. Yes, absolutely. CIS patients may evolve into RRMS, and the majority of RRMS patients transition into SPMS over time. The precise timing of these transitions is challenging to ascertain because they are often based on the subjective recollection of symptoms and interpretation of signs. Secondary and primary progressive MS share many MRI features and pathogenic similarities. If we could instead delineate well-defined subtypes that are aligned with underpinning pathobiological changes, we would be able to identify subgroups to which treatment mechanisms do or do not apply and address these long-standing ambiguities. Now that's exciting. MRI is a strong candidate for data-driven disease classification because it better reflects the MS pathogenic mechanisms than purely clinical descriptions. So while the last paper we looked at was considering blood and the data that the machines could interpret based on blood samples, this is looking at MRI samples. But it's looking at them across the board and from people in all different stages of the disease And it's very objective data, which is what machine learning is really good at processing. They go on to say neurodegenerative disorders have a long prodromal period, so a period before the disease is actually recognized, and are lifelong. A key barrier in identifying subtypes of these disorders is to stitch together observations from cross-sectional or longitudinal studies, which are rarely more than a few years long. That has been a problem because, of course, our symptoms take a long time, years and years, to really develop, and most clinical trials only last a few years. So the effects that they're looking for may or may not even show up. That doesn't necessarily mean that they won't show up. So it's hard to make a conclusion that's definitive with clinical trials that are limited in that way. Grouping individuals on the basis of a similar appearance on a single time point or MRI is not sufficient, as patients belonging to the same subgroup would show different abnormalities as their disease evolves and would appear different. They seem to really understand MS and how unique it is from person to person. We have recently developed an unsupervised machine learning algorithm called subtype and staging inference to uncover data-driven disease subtypes with distinct temporal progression patterns. This ability to disentangle temporal, that's time-bound, and phenotypic, that's how things look, heterogeneity, differences, makes sustain different from any other unsupervised learning or clustering algorithms. The algorithm identifies a set of subtypes in the training data which can be cross-sectional. Each subtype is defined by a pattern of change in a set of features such as MRI abnormalities. Once the sustained subtypes and their MRI trajectories are identified, the resulting disease model can determine how closely a patient whose MRI is unseen belongs to each subtype and stage. So this is the real beauty of this technique, is that you can predict something about a patient without having to actually see their MRI. And they go on to say, here we aimed to redefine subtypes of MS data on a data-driven assessment of the pathological changes visible on MRI scans rather than the evolution of clinical systems, with a view to targeting therapies to subpopulations who share pathogenic mechanisms. In this manuscript, we use phenotype when referring to standard clinical phenotypes, relapsing MS, primary MS, and secondary MS, and subtype when referring to MRI-based subtypes identified using sustain. We applied sustain to a training dataset from previously published clinical trials and observational MRI studies, as you can see in Table 1, to define subtypes that optimally explained the temporal and phenotypic MRI heterogeneity and then validated them in an unseen, independent set, thereby confirming the generalizability of the model. Our secondary aim was to determine whether there were differences in progression of disability, disease activity, and treatment response between sustain-derived subtypes at study entry. Let's just take a quick look at this table if it's possible. So here's just a bit of the table. I won't go through this in any detail because most of this is probably beyond what any of us are really interested in. But I think the important things to see here are, for one thing, in the left-hand column, you can see that they got their data out of clinical trials that had already taken place. In the second column, it's really neat to see that they're not just going with one type or, the recognized types of multiple sclerosis. There's some that are mixed, there's some that are with relapsing, some with secondary progressive, and some, as you can scroll down further, you can see there's some with primary progressive. And then they go on to talk about the types of studies, the participant numbers, the visits, the MRIs, the published protocol citation number. That's all stuff that we don't need to really get into in any detail, because I think those first columns are what tell us how exciting this might be for us. And I'm not going to go through the results in great detail. That's going to have a lot of terminology and detail that we don't really need to see, but I'm going to link the paper down below. you can certainly go out and take a look at it, because there is some good stuff in here. And if you enjoy looking at statistics and you want to know all those details, it's certainly available to you. And there's the methods. We definitely don't need to be going through all that, because that just tells you how they set things up. And that is very important in a peer-reviewed paper, because they need to make sure that their results are achievable, because their experiment is replicable. They can reproduce the conditions of the experiment in order to get results. And that way other scientists, other teams of researchers can validate that. And their data will be made available upon request to those scientists who want it. And I actually did find some other studies, but I'm just going to take a real quick look at the abstract for this one that I found through PubMed in the National Library of Medicine. It was originally published in 2020, so this research is not brand spanking new, I have to say. They've been looking at this for a while. And the title of this article is Prediction of Disease Progression and Outcomes in Multiple Sclerosis with Machine Learning. And as we scroll down here, we've got some researchers. Let's just check the affiliation to see where they're from. And these folks, as it looks like, they're in Portugal, or at least the lead author is. And that again is heartening, because that tells me that this is being looked at in more places than just one country and one team of researchers. Well, if we could take a look at just the abstract, it says that multiple sclerosis is a chronic inflammatory disease affecting the central nervous system and leading to irreversible neurological damage such as long-term functional impairment and disability. I think every paper kind of has to start out with that, just to kind of set the stage. But we know that stuff only too well. It has no cure, and the symptoms vary widely depending on the affected region's amount of damage and the ability to activate compensatory mechanisms, which constitutes a challenge to evaluate and predict its course. So that's kind of the problem that they're looking at trying to solve. How to evaluate and predict the course of MS. Additionally, relapsing remitting patients can evolve into its course into a secondary progressive characterized by slow progression of disability independent of relapses. With clinical information from multiple sclerosis patients, we developed a machine learning exploration framework concerning this disease evolution, more specifically to obtain 3 predictions: 1 on conversion to secondary progressive course, and 2 on disease severity with rapid accumulation of disability concerning the 6th and 10th years of progression. For the first case, the best results were obtained within 2 years. And for the second, the best results were obtained for the 6th year of progression, also within 2 years. The expanded disability status scale value, the majority of functional systems, affected function during relapses, and age at onset were described as the most predictive features. These results demonstrate the possibility of predicting MS progression by using machine learning, which may help to understand this disease's dynamics and thus advise physicians on medication intake. So kind of the same objective, the same goal of the research is to help physicians diagnose and predict the future of folks with MS. But this one, as you can see, because it's now several years old, you can see in a way, don't you get a sense of how much machine learning as applied to MS has evolved just in 3 short years? It seems to me that scientists have a lot more understanding that the answer is yes, this stuff will work. And then looking at different sources of data, looking at MRIs, looking at blood, looking at different ways to give the machine the data it needs to make those predictions. So I liked seeing the course of this. I like seeing how widely dispersed and distributed the research teams are. I feel like there's a lot more interest in this kind of stuff than I ever even realized. So again, I'm wondering, why have I never heard anything about it? Well, it's been going on for quite a while, so it's interesting that I only just found out about this. And I'm going to be watching it, believe you me. I'm also interested in how this dovetails with Gavin Giovannoni's position, which I totally agree with, that MS is not all these different diseases. It's one disease that has various presentations. And I can't help but wonder if the same machine learning couldn't be applied to all phases of MS with some benefit. I will be keeping you posted if there are new updates and if I ever hear of any doctor actually using this, because I'm kind of wondering if it's not ready for prime time yet. I've never heard a thing about it. If you have, please let me know in the comments. I'd be really interested. Well, that's all I have for you today. So I will see you again in my next video, but in the meantime, take really good care of yourself.